SU-ERP is a multi-tenant university ERP. One deployment serves many institutions, each isolated at the row level. It's built as microservices, a Django services plus one fast API ML service, talking to each other only through events on RabbitMQ, sitting behind an Nginx gateway. Front end is Next.js. Everything you're about to see is real. No mock data, this is the actual system, running locally. Before any student or staff exists, a superadmin provisions the institution itself. This is the only cross-tenant screen in the system. Everything else is locked to one tenant by a claim inside the login token. Every other login is tenant-scoped. Institution slug, email, password. The slug picks the tenant. Auth service issues a signed token with a user ID, role and tenant baked into it. There's no gateway that vouches for you. Each service verifies that signature itself. Zero trust, admin dashboard, live counters for users, invoices, allocations, and tickets, all scope to this one institution. Fee structure management, Hostel block setup, and the full user roster, Warden, faculty, driver, Canteen owner, students. Admin can multi-select and bulk deactivate users. It's a soft delete, not hard delete, so the row stays for audit. 2 guardrails are enforced on the server. You can't deactivate yourself, and you can't remove the tenant's last active admin. Onboarding is a single add form, or a CSV bulk upload for a whole cohort in one shot. This next part is a distributed saga across 3 services, Hostel, Finance, and Notification, coordinated entirely through events. No service ever calls another directly. Watch the sequence. The student browses available rooms and submits a request. The warden approves it and picks a fee structure. This calls the exact same allocation path as a direct bulk allocate. Approval is just another entry point into the same saga. Under the hood, Hostel service just emitted an allocation requested event, and Finance service consumed it and raised an invoice, with no direct call between them. The student pays. Finance emits a payment success event. Hostel correlates that back to the original allocation by invoice ID and confirms the seat. Notification service picks that up and writes the student's inbox message. 4 services, 1 business transaction, and none of them ever blocked on another's uptime. Because payment succeeded, a PDF receipt was generated with a signed verification token, rendered as a QR code. A warden or admin can scan that QR code here. It's HMAC verified and tamper evident, cross-checked against the server. This is a real receipt, confirmed valid. This saga is order independent. Even if the payment event arrives before the invoice event, it still resolves correctly, and it's idempotent under redelivery. I stress tested it separately, 50 threads racing for 1 seat, using real Postgres row locks, and exactly 1 thread wins. I also killed RabbitMQ in the middle of a live saga. The write still succeeded, because the event is written to an outbox table inside the very same transaction as the business row, instead of being published inline. When the broker came back online, the backlog drained itself automatically, no manual replay, no lost events. Second saga, a grievance, scored by a dedicated machine learning service, automatically escalated to the warden if it's serious. The student files a ticket. Grievance service emits a created event, carrying just the free text and who raised it. The AI service, which is fast API rather than Django, because it's a pure scoring endpoint with no need for an ORM, consumes it. Scoring is VADER sentiment analysis plus keyword-based urgency rules, deliberately lightweight, no heavy transformer model, so it runs on a laptop. Safety keywords like fire or ragging push urgency straight to critical, regardless of the sentiment score. The AI service emits a scored event. Grievance service auto-escalates high and critical tickets straight to the warden's queue, and notification service writes the student a message. Same event-driven pattern as the Hostel saga, completely different services. Canteen is a fully separate service, unrelated to Hostel or Finance business logic, but it rides the same rails, menu management, and orders queue with a real status machine, placed, preparing, ready, completed, and checkout goes through the same payment integration students already use to pay Hostel fees. One payment concern, reused across 2 unrelated domains. Faculty and driver logins exist and are fully tenant and token aware, but exam, attendance, and full transport logic are intentionally stubs for this pass. working CRUD prototypes on the same foundation, not full business logic. 8 services were built deep, rather than 13 services shallow, because the saga and the ML demo needed real depth to prove the architecture actually holds up under concurrency and failure, not just on the happy path. Same login screen, different slug, completely disjoint data, different rooms, different invoices, different users, despite sharing the same posters instance and the same tables. Isolation is enforced by a custom manager that scopes every query to the tenant in the current requests token, not by convention, and not by the front end being careful. Every Django service exposes Prometheus metrics, request rate, latency, error rate, and per tenant request count. This capture is from a real load run, around 2,800 requests at roughly 10 a second, across 2 tenants, with a P50 of 10 milliseconds, a P95 of 34, and 0 server errors. That run is also what caught the gateway's rate limiter working, and the auth services lockout working, correctly rejecting abuse. To summarize the engineering, not just the interface, multi-tenant with row-level isolation, zero trust authentication verified independently by every service, sagas built on a transactional outbox and an idempotent inbox so no event is ever lost or double processed, tested under real concurrency, not just unit tests, and observable in production with Prometheus and Grafana. Code, tests, and the full CI pipeline are all in the repository.